Okay, let's a few words about the test and then we'll dive into chapter 11. So the test, the average was 45 before the curve. A 36-point curve was added to bring the average up to 80. So this was slightly lower than my average test. It was a little bit too long. I graded the last problem, and judging based off of how many people got to it and could give it a real shot, the test was a little bit long. Before the curve, the MSc students had an average of 51 and the high score of an 80%. The mechanical engineers had an average of 44, but the high of an 89, which is about average. Mechanicals always get the high. MSCs usually beat the average by a few points. So it was standard performance, I think, in terms of tests. So again, the score that you see on Canvas is the one with the curve added. Always good idea to make sure that we added these things up right. We do so at 10 or 11 at night when we're finally adding them up. So make sure that we gave you all the points that you're entitled to. And if you do have a question on how something was graded, let me know and we can take care of that. Just come up after class. But question now?
What's the point of having a test where the average is a failing grade?
Good question. So the answer is that it is very difficult to write a test which is neither too hard nor too easy. That's really the takeaway. It's very difficult to figure out how long questions are going to take when you're so close to it. So for that reason, I have the TAs take it and give me an estimate on timing. And this one turned out to be a little bit on the short side. So it's never a goal to have a test where it's that, right? My goal is to have the average so I don't have to apply much of a curve, right? But it does happen, and you're still graded relative to your peers, right? And the average is still brought up to well above a passing grade. So I feel like it's still a fair approach. So I'll just say that it's difficult to write a test that the average will lie exactly at 75 or 80%. That's very difficult to do. Yeah, Arthur?
Can you just remind us at what percentage you bring the lowest midterm?
Good question. So for those of you that are still in this class, so mechanicals and materials, there are 3 midterms and a final exam. How I do it, instead of making each midterm worth 100 points, I take your worst midterm and I scale it by 25%. And I take your best midterm and I scale it by 175%. This doesn't have the exact same effect of dropping a midterm, but it pretty strongly does. If you have a bad day and you really make up for it on a future exam, it can really pick up most of the points that you lost. And then your medium midterm, I don't adjust at all. It gets whatever points you earned on it. Other questions on midterms? Yeah.
A little different but related. So your policy for the final, if I'm not mistaken, right? It's if the grade on the final is higher than the grade in the class, just so everyone remembers. Then that becomes your grade in the class, right?
I do not have that policy.
Okay,
other faculty do. I don't have that one.
Never mind.
Other questions? Yeah.
So when the civil engineers prepare final exams, do not will ours be?
Good question. Ours will be cumulative. So the final exam is 2 hours rather than 1 hour. So you can expect 6 questions rather than 3. And because there are chapters we haven't covered yet, they'll get their own problem for sure, right? Chapter 11 and chapter 12 and possibly chapter 15, composites if we get to it, those will all likely have their own questions. So a question on kinetics, a question on electronic properties, possibly one on composites or sustainability. And then the other 3 will be reviews, right? Taken from the rest of the semester. Free energy, electrochemistry. Probably won't repeat an exact question, right? So we've done a Weibull question. I probably won't put another one on. That said, you'll see a study guide well in advance of the final exam, so you'll have a chance to know exactly what's going to be on it. Yeah, Arthur?
Are we gonna can we get a longer review?
Can you get a longer review? Like, what do you mean? The night before review sort of thing?
Yeah. Like you used to do reviews until the last midterm.
Yeah, this last one I would normally have done. I had travel that prevented me from doing it. This upcoming final exam, I will of course do another evening review. It'll probably just be the 2 hours like normal. But I'll see if the TAs can also hold 1 or 2 reviews themselves. Okay, other questions? Okay, let's keep going. All right, so new chapter. We're leaving behind our diffusion of both mass and heat, and now we're moving to kinetics. Kinetics, I think, is interesting because up until now, we've described things as they ought to be, meaning from a thermodynamic, when it reaches equilibrium standpoint, we know what things should be. If the delta G goes positive, then it doesn't happen. If it's a negative delta G, then it does happen. This chapter turns that a little bit on its head because it says there's another thing that we have to consider. It's not just thermodynamics, it's kinetics, right? It's kinetics and kinetic barriers to something happening that you would expect to occur from a thermodynamic standpoint. So that said, our learning objectives are first, we're going to identify the driving as well as the limiting forces for homogeneous nucleation. We will calculate the overall change in free energy as a function of solid embryo size, shape, and other parameters. We're going to use the derivative of this free energy expression to determine what the critical radii size is for nucleation and growth. Right? We'll then calculate overall rate of transformation for nucleation, and we'll even figure out, we'll be able to calculate by the end of class, how much should something undercool or supercool, meaning how much below the temperature where you expect it to change, will it actually change? And if we have time, we'll then transform that approach to heterogeneous nucleation and talk about what are the differences between homogeneous and heterogeneous nucleation. Okay. So we already have talked at great length in this class that the microstructure matters, right? The microstructure, meaning what type of grains, how they're oriented, are there grain boundaries, are there dislocations? All these things are encapsulated under what we call microstructure, right? And we've even given ourselves some tools to predict microstructure. Things like phase diagrams. They tell us whether it's going to be a lamellar structure, whether things will precipitate, whether it's going to be molten. But they don't take into account kinetics. Meaning, phase diagram assumes that you reach thermodynamic equilibrium, which means long times and plenty of temperature for things to move around. But that's not the world we live in. The world we live in has kinetic limitations, meaning something might go really slowly. It might be diffusion that just isn't fast enough to make it happen. Or there might be other barriers, right? So before we get into that, so I guess the end of this chapter, we'll talk about kinetics more in the case of steel. We showed you a steel phase diagram. By the end of this class, we'll talk about all the different quenching that they do to steels, and we'll talk about what structures those produce, because it's actually quite different. So when we talk about kinetics, they are kinetics of phase transformations. So one phase turning from one to another. That can be solid to liquid, liquid to solid, but it can also be a solid precipitating out a secondary phase, right? Like in the case of steel, you start out with pure austenitic steel, austenite, and you turn into cementite plus ferrite. So we're going to talk about those phase transformations, and there's three types. The first one is diffusion dependent, but the composition doesn't change. Diffusion dependent means you have to have atoms moving, right? But the composition isn't changing. The other one is diffusion dependent, but the composition does change, right? And then our last one is no diffusion, but a metastable phase is produced, right? And we'll give some examples by the end of this, okay? So regardless of which type of phase transformation we're talking about, they always have a few things in common. The first one is that you're going to start out as small particles. We call these nuclei. You nucleate small particles, and then these grow, right? They grow to some final size. They might completely replace it, or they might grow to just some stable nuclei size. There are two ways that this can happen. The first being homogeneous nucleation, homogeneous. And in that case, these nuclei form, let's say deep within the material. If you've got a big bucket of water, right? And if an ice crystal is going to form, it can choose to form right in the middle of that water bucket, or it can choose to form at the edge of the bucket, right? That's the difference between homogeneous and heterogeneous nucleation. Homogeneous means it happens right in the middle, and heterogeneous means it's happening not in the middle, but at some sort of interface or surface, right? And the fact is that these inhomogeneities, be they surfaces, insoluble particles, or whatever else, they often reduce the energy barrier for nucleation, which is why if you've ever noticed where ice forms, it forms at the edges of things, right? It's rarely that you're just seeing a bucket of water with an icicle or a little iceberg that formed right in the middle. It formed at the edge and broke off and then moved to the middle maybe. Yeah, Brendan?
So are homogeneous formations more common in like liquids and gases than in solids?
Good question. We'll see examples of homogeneous nucleation. In fact, next class period, we have a really sweet demo of it, where you'll see the difference between homogeneous and heterogeneous. But I'd say if you wanted to encourage homogeneous nucleation, then what you'd want to do is you'd want to limit the inhomogeneities, things like surfaces, insoluble particles, grain boundaries, etc. If you limit those, make sure there's fewer of them, then your odds of getting homogeneous nucleation goes up. Yeah, Rob?
This is why things like boiling need like sites, right? Or like seeds to start with, right?
Yeah, or why maybe I don't know if you've heard of this. There's I used to think it was an old wives' tale. We've reproduced it though, it works. If you take a really smooth teacup, right, you fill it full of water and you nuke it in the microwave for a while.
Explode, yeah.
Yeah, you've seen the YouTube videos of this, right? When they stick a spoon in it, all of a sudden it just like bursts into steam everywhere. Like it doesn't explode, but it generates a lot of steam. That gas pushes water everywhere. It looks like an explosion, right? So we've actually reproduced that. It does happen. And in that case, the wall of the ceramic teacup was really smooth. There weren't like bumps or edges or impurities that made it easy for gas bubbles to form. But when you stick a spoon in there, that jolt when you initially put it in, that does create inhomogeneities, which encourage heterogeneous nucleation. We'll see, like I said, 2 examples of this next class period that are pretty neat. Okay. So let's dive into homogeneous nucleation. This means that we're ignoring all of the boundaries on the outside. We're basically considering this. We're saying, okay, you've got some matrix phase A, alpha, right? That could be a liquid at some whatever composition you want. That could be a pure material or a mixture, right? That could be a copper-nickel mixture. It could be pure water. It could be whatever. But that's going to be, say, liquid. And within that, right in the middle, we're going to form an embryo or a nuclei of some other phase. Let's call it the beta phase, right? And this thing has a radius r, right? So this is the setup for homogeneous nucleation. Again, the phase transformation that we're interested in here is alpha going to beta. So if you did your thermodynamic calculation, you would say that the free energy for this reaction, as written, we would say that delta Rg for that reaction equals negative. Right? It's a negative number, meaning it wants to happen, okay? So the change in free energy, delta G, is going to be the free energy of the beta phase minus the free energy of the alpha phase, right? And again, we said that's negative, so it wants to happen. Now, when you do these problems, it's convenient to convert free energy on a molar basis, right? We've been talking about free energy, like, for example, this could be negative 100 kilojoules per mole. It's been useful to talk about it in kilojoules per mole basis. In this chapter, it's going to be useful to convert it into a molar volume basis, right? So what we do is we take, and to turn our free energy into a volume one, all we have to do is we divide the regular free energy by the molar volume, right? So if we take this and we divide it by whatever the molar volume was, something in, let's say, meters cubed per mole. So however much the volume is per 1 mole of substance, per mole, then the moles cancel out, and we're left with just kilojoules per meter cubed, right? So it's the free energy on a volume basis. I'll show you why that's important in a moment. Any questions so far? Okay, let's keep going. So how about this? If there's a change in free energy from one phase to another, and it's negative, why is there any resistance? Why are we talking about resistance at all, right? Shouldn't it just be automatic? Up till now in this class we said, yeah, it's automatic. If it's free energy is negative, it's spontaneous, meaning it just happens, right? So why doesn't it mean that? So turn to a neighbor and discuss what could possibly be going on that makes this not negative. Okay, let me pick on David. What do you think? What might be going on?
So I would think that it has to do with that that energy change has to occur for all molecules. So it has to there's probably collisions and stuff that is restricting the ability of the energy to transmit through the material. Okay, good guess. Yeah, basically the transformation we went up before, we said these transformations, there's different types. Some of them require diffusion, some don't. Right? What if maybe what you're saying is that, okay, you've got all these atoms that want to switch and they have to move around. There could be some kinetic limitation to that. Is that what I understand you're saying? Yeah, that can happen, absolutely. What else? There's another big one. Anybody want to throw out? Thomas, what do you think?
The temperature. Someone's raising the temperature.
Yeah, so we can calculate, good point to bring up, we can calculate the change in free energy for a reaction, delta Rg. We can calculate that for any temperature we want. Let's assume that at this temperature, delta Rg is negative. Okay, so temperature is taken into account of basically in delta G. So what else might there be happening here? Anybody else want to throw something else out? There's one more big one left in the back. Is it Spencer?
Yeah, maybe you get more surface energy, getting bonds and things when you're moving.
That's exactly it. When you create a new phase out of an old one, you create a surface energy, right? So take a look at this. We had pure alpha before in this vessel. The surface energy in that was basically whatever it was lining the container with. But when you nucleate a new phase, this embryo, that has a surface area associated with it. It can be big or small, right? Depends on the size of that embryo. But that surface energy we know has a penalty. So you have to take that into account, and that's really the fundamentals of homogeneous versus heterogeneous nucleation, is the difference in the surface area that it creates. So let's start with it. So this barrier resisting nucleation is that surface energy created. So let's start with the simplest model, which is a spherical model. Our embryo is going to be a little sphere as opposed to some other weird shape. On the homework that I'm going to assign, you'll do some sort of weird shape. You'll do like a triangle or a pyramid or something like that, some sort of non-spherical shape. And it's the same approach, but use different geometric calculations. For a sphere, let's say it's like this. Our change in free energy, the overall change in free energy, it's going to be equal to the volume of a sphere, which we know is just pi r cubed, right? We're going to take that volume and we're going to multiply it by the change in free energy on a volume basis, right? So on a per meter cubed basis, we're going to multiply what do we expect the free energy change to be? And again, that should be a negative number, right? But then, so this term, because that's a negative number, this whole term is negative. We're then going to add to it this term over here, 4 pi r squared. That's the surface area of a sphere. That's our surface area of a sphere multiplied by the surface energy, which we're going to call gamma. Okay? Question, Takar?
No, you answer.
Okay. So this term on the left is negative. This one on the right is going to be positive. So now all of a sudden we can have this competition we've been describing. Before we said, okay, you've got negative free energy, you expect this thing to happen. Why would it ever not? Well, now we see why it might not, because you have a negative component and a positive component in competition with one another. So the question is, if you have one going as r cubed, right? One depends on the size of the embryo r cubed, and one goes as r squared. Which one wins in the short term versus in the long term? So we'll turn to Wolfram Alpha for this one. And all I've done here is I've asked Wolfram Alpha to plot a negative r cubed plus a positive r squared, and we're going to plot that over some small distance. And in a second, it'll do so, and this is what we see. So here's our overall plot. It starts out at 0, right? As r approaches 0, both those terms go to 0. But as you increase r, initially, what happens is that your r squared term is winning. R squared grows faster at first, right? So it's actually going up in energy. What does this mean? It means that as you take the atoms that create the beta phase, as they clump together and form, say, a solid out of the liquid, they clump together, and at first, every new atom you clump together, it's going up in energy, right? That makes sense? It's going up in energy at first, and you get over this critical point here, and then you start to go down, and then it always goes down in energy. The negative r cubed term wins in the long term. So this interplay, and basically that there's a critical distance, is what describes why homogeneous nucleation occurs. Okay? So let's sketch it ourselves. Again, if you're plotting change in free energy, delta Rg, for this reaction, right, taking into account surface energy, then at first it's going to go up, and then it's going to go down all the way until large values of R, right? So again, this is plotting as a function of not interatomic separation, plotting as a function of your nuclei radii, okay? The size of this little embryo, okay? So because of that, again, this leads to important things happening. Basically, at first, when you clump more and more atoms together, you go up in energy. If you were to stop and hit pause right there and ask that particle, is it happy with its arrangement? It would say, no, I'm not happy with my arrangement. I'd rather dissolve again. I'd rather take all these atoms that created the beta embryo and tell them to get out of here and turn liquids again, right? And they go back down. They would redissolve because it can lower its energy by dissolving. Make sense? But every once in a while, you get enough of these atoms that collide together that they get past some critical size, which we're going to call R star, right? Enough of them bonk together all just at once, and now they're larger than R star. And now if you're on the right-hand side of this point, it actually becomes more expensive in terms of energy to start shrinking, and it becomes less expensive in energy. You go down in energy to keep on growing. Make sense? Because of this, we have something we call the critical embryo radii size, or nuclei radii size, wherein if it's larger than that, it will grow, and if it's smaller than that, it's probably going to just dissolve again. Yeah, Anders?
How does a reaction like this even start if it's going up in energy and wants to stay?
Great question. So you have thermal energy, right? And so because of thermal energy, atoms are moving around all the time. We know that, especially if it's in like the liquid form. They're moving around all the time. And at any given moment, they're going to clump together in an arrangement that looks kind of like a solid. And if the size of that clumped atoms is larger than your R star, it now says, hey, rather than dissolving, what if we just keep on adding atoms? We go down in energy. So it has to do with thermal energy. So obviously, the higher the temperature, you'd expect more diffusion, and we're going to come to the role of diffusion there, versus the role of supercooling, which is how low below the temperature are you? For example, let's say this is liquid gold turning into solid gold. Thermodynamics says that happens at some temperature, I don't know, 1,000 C or somewhere around there. By the time that you supercool it all the way down to, say, 800 Celsius, it might be really, really likely to solidify. But if you're only 5 degrees below, it's less likely. So we're going to introduce a term that accounts for temperature. Yeah, Zach?
So if that's correct, like rainwater wouldn't precipitate naturally without current like radius too.
Absolutely.
Like probabilistically, you can't get enough molecules together.
Understanding homogeneous versus heterogeneous nucleation with rain is a very big deal, and it's big business, because what they do is people realize that. They said, okay, the likelihood of water in the vapor phase to come together and look like water in the liquid phase and have a droplet that's bigger than your R star is not a huge number. It's kind of rare. I mean, storms can happen, they do happen, but it's not as common. But what you can do is you can add a seed crystal. You can seed rain clouds and make it rain. You can make it rain. Right? So we will learn about making it rain soon. Okay. One more thing to mention here from this plot. You have this value right here at the top of this free energy curve. We're going to call that delta G star. Delta G star. And you can think of this as an activation energy. Basically, if your particles, as they are moving together and as they clump together, if they came together with enough energy to overcome that activation energy, that's another way of thinking about that they were a large enough size that they were larger than R star, right? So there's an activation energy or a size, a critical size radii. Either one of these is an appropriate way to think about whether or not something will keep growing or just redissolve again. Yeah, Rosa?
Is there any benefit to like trapping the atoms like right at R star?
Is there any benefit to just holding them right there, where it's sort of like in this metastable state where it could either go back or forward and it would go down?
Is that where we trap like our metal when we
Good
in
question.
the lab and has to heat it up against the hands to make it back down?
Great question. No, it isn't. But what we did do is we lowered it way below the temperature where it wanted to transform, but we did so quickly. So basically what we did if you remember in the class where we brought in all the different shapes of metals, we held it in our hand and some of them got warm. What we were seeing is that at that point, the delta GV term was very negative. It really wanted to transform from a single phase to a two phase, but doing so would require creating surface energy. So by quenching it, this term was large, and then all you had to do was hold it in your hand and give it some of your thermal energy. And what you did is you gave it enough energy that it could climb up temporarily. Once it got past that, then it's favorable to keep on growing. So kind of like it. Pretty similar. Yeah, Rob?
How does something like seeding factor into this? Would you just add it to the radius, like the radius of the seed to the radius of...
Hold that thought. We're coming to it. That's heterogeneous nucleation. By the end of class today, or maybe next class, we'll get to that. Yeah. Connolly?
You can talk about it in terms of like an activation energy. When like if I'm at the tip of it, then I'm just in the middle, but like if I'm below that, I don't know which side to grab it on.
Yeah. Right at the very top is tricky because there you don't have any activation energy because either way you go is down. But let's think of it back in terms of diffusion. Diffusion, we said if you were to plot, say, energy as a function of moving around in the lattice, maybe you've got one site right here and another site right there. And we said that there was this activation energy. I should draw this so they're equal, right? If there's no chemical potential driving force, meaning no concentration gradient, then the atom that starts out right here, if he can overcome this activation energy, then it could end up right there, right? And the bigger that activation energy, the slower your diffusion. So think of this in kind of the same way. In order for these particles to clump together and keep on growing, they've got to overcome some sort of activation energy, okay? Any other questions on this? Okay, let's keep going. Okay, so this plot, again, it physically means that if your cluster, when it comes together, is smaller than R star, it's going to shrink and redissolve. And if it's larger than R star, it's going to keep on growing, which we've been saying. Okay? So that's interesting from a theoretical standpoint. How do we actually calculate this thing? How do we calculate R star so we know how big it needs to be? Well, we can do so, right? First off, we know it's going to be at the maximum of this delta G curve, right? You have this delta G curve, goes like this. A maximum, we can figure out from calculus, a maximum corresponds to a zero of the derivative, right? So what we're going to do is we need an expression for this curve, delta GR. So delta G as a function of R, which we have. We figured that out up here, right? Here's our expression as a function of R. We take the derivative with respect to R, set that equal to 0, and that should allow us to solve for the critical radii size. So that's all we've done here. Down here I'm taking the derivative of delta G with respect to R, right? This was our surface area before, was 4/3 pi r cubed. That pi r cubed becomes r squared, and we bring the 3 down because we took the first derivative, right? The surface area term, this used to be 4 pi r squared. Taking the derivative, the 2 comes down, right? So all we've done is we've taken that expression, taken one derivative, set it equal to r, and when you solve for r now, or set it equal to 0, and when you solve for r, you get that it's -2 times the surface energy divided by delta GV. Or in other words, if you have a really big surface area penalty, then you have to reach a really big critical radii, right? The bigger gamma is, the bigger r is. And if you have a really big difference in free energy, then the smaller r is, right? The bigger your driving force in terms of change in free energy, the smaller that critical radii needs to be, okay? Those should be intuitive, should make sense. Thomas?
Is gamma a constant?
Gamma is going to be a constant for your material. It's going to be a surface energy, right? Now that very well, it will have a temperature dependence, but that's your surface energy. It's basically a measure of how much energy. This thing is going to have a measure in joules, say per meter squared, and it's just measuring how many broken bonds are there, right? Is there a lot? Is it costing lots of energy or not to form this new surface? Rosa?
So that first derivative equation, and then you have the R star, delta G star. Are those both derived from that derivative equation?
Yeah, this equation right here, if you turn around and solve for R, you literally get this expression.
So solving for R, you get R star, and solving for G, you get.
And then plugging in R star in here, that gives you delta G star, right? So if you go back up here, delta G, if you plug in R star, that gives you delta G star, which is just the height of this at its maximum.
So you have to, with the derivative, you have to solve for R star, find the value, put it in the R star equation, and then put it back into the derivative.
Into the original
To the original.
to get delta G star.
So you get delta G star by taking the R star from the derivative and putting it in the original.
Bingo. Yep, you got it. You got it. This is all with a spherical particle, right? You could do this exact same thing assuming that your particles are cubic. You know, cubic crystals exist in nature, form all the time. Salt, right? Salt forms little cubes. So you could redo this, and instead of using the surface area and the volume of a sphere, you do it for a cube, right? Similar approach, similar kind of looking terms. Your constants are going to be off by a little bit. So one of the homework questions, I think I'll have you do that, okay? Either for a cube or for a pyramid or something weird, okay? So we can do more with this. Let's now take into account and let's figure out what is our total change in free energy, again, accounting for what we expected from thermodynamics plus what now we know is limited due to surface energy. Let's calculate that change in free energy as a function of temperature. Particularly, we'll do it as a function of how far below the temperature we are from where we expected it to change. So again, if we go back to phase diagrams, any phase diagram, let's say we expected something to happen, I don't know, you expected it to go from a liquid to 2 different solids right at that purple point, but in reality, you're able to cool below it. Let's say you're able to cool away all the way down to there, and then it transforms, right? That's basically what we did with our demo, right? With the piece of metal, they were in one phase, it wasn't a liquid, it was a solid, but it's converted to 2 different phases when we supercooled it a certain amount below. So what we'd like to figure out is what does the free energy do as you go below that? The further down you go, how do we come up with a term for that, an expression for that? Okay, so we go back to our delta G, and first off we recall that we can write that in terms of entropy and enthalpy, right? Furthermore, let's see, so you can solve for entropy in terms of the heat of formation, right? This is your change in enthalpy of formation on a molar basis. V again is our molar volume. It's how big your 1 mole of your substance is in terms of volume. And now delta T, that's going to be the amount of undercooling. So it's going to be a positive number, that represents how far below the solidification point you are. So again, if this was ice, water turning into ice, we know that should happen at 0 Celsius. Let's say you're cooling down water below it, you supercool the water down to -5. Then your delta T would be +5 degrees, right? That's your difference. That's how much supercooling. So again, don't get hung up by the negative positive thing. If you're below it, we use a positive number, and it's the amount of degrees below the temperature we expect it to change at. So again, if your transition between alpha and beta, you expect it at some temperature, but you're below it, then you're supercooled, okay? When you take that into account, now you modify your R star expression slightly, like so, and you modify your delta G star expression. So your activation energy for nuclei formation, or your critical nuclei size, these get modified. And basically what you're going to see is that the bigger this number is, the temperature where you expect it to change, and the temperature where you're at, the bigger that number is, the lower your radii size is going to be, right? Yeah, question, Thomas?
Temperature at equilibrium is the temperature of alpha or beta?
Yeah, assuming just thermodynamics, right? So again, going back to our phase diagram, what these lines are, all of these lines is our lines of phase transformations, right? Here you've got solid and a liquid turning into pure solid, right? So at any composition, this line is telling you that T, I guess alpha L in this case, right? It's telling you where you expect it to transform, right? But in reality, you can go below it, you can supercool it because the formation of surface energy sort of retards this process, right? So let's go to here again. And again, scroll back down to this. Okay, the bigger this number is, the smaller your R squared. The bigger this number is, this time squared, it greatly reduces the activation energy you need. So let's sketch this. I think it's easier when you sketch it. So again, we're going to plot now energy against the critical, or well, the nuclei size R, right? So this is change in energy. And we're going to do so for two different temperatures. One temperature is not very far supercooled, and so it's got a pretty big activation energy. And we're going to do it for another one, which is supercooled quite a bit, and it has a smaller energy. So this one, it reaches an R star value at a low value, whereas the other one, since it's not as heavily supercooled, its R star value is larger. So again, we'll call this 1. That's 1. We'll call the other one 2. That's 2. So we know then that temperature 2 is less than temperature 1, which is less than the transformation temperature. Any questions so far? So, yeah, Rosa?
So, is this saying that it takes, like the blue one, the first one, that takes more energy because you haven't cooled it enough to make the radii smaller?
That's one way to think of it, yeah. Yeah, that's the correct way to state it. Again, it means that you have to get enough atoms together that they're larger than R1 star, right? Because it's just not very supercooled. The more you supercool it, the bigger that driving force in terms of delta GV is, and your surface area is not changing, right?
So the size of the atom changing?
No, your atom size isn't changing. This is the size of the cluster of atoms that come together to form your new phase. And so far, we're just talking about liquids turning into solids. But this you could also do for solids turning into other solids. Liquids dividing into two different immiscible liquids. You could do it for any of those. It's just easiest to think of a molten something turning into a liquid. Yeah, Arthur and them, Thomas?
So the R and the delta G is proportional. It's kind of like you can have a curve that has a very big R but a very small delta G.
You can. We'll get to that. Right now it's proportional. With homogeneous nucleation, it's proportional, meaning this value, delta G star, we'll call that 2, that's small because R squared, or R star 2 is small. And again, this point up here, which we'll call delta G star 1, that's large because R1 star is large. And again, that's large because we're not very far supercooled. If you really supercool it down further, both things get smaller, right? You have a smaller energy barrier and you have a smaller critical size. Make sense so far? Yeah. Supercooling means that, let's say you're at a phase diagram and you expect the transformation to occur at this point, this purple one here, like we're talking about maybe the eutectic reaction. You expect that to happen at, I don't know, TE, whatever that is. But in reality, you notice that you can go in the lab right now and you can make this stuff, and when you cool it down, you've got a thermometer in there, and the thermometer says, hey, I'm below TE. I'm clear down here at like, I don't know, T1, T2, which is less than the eutectic. So from a thermodynamic standpoint, you think that should have crystallized. That should have transformed into a mixture of alpha and beta, but we've still got liquid in this region where we didn't expect it. This is the whole point behind the kinetics chapters, that it disobeys what we expect from just considering thermodynamics. Okay? Yeah, Rosa?
One.
Yep.
Why do the little clumps get smaller when you cool it more?
Good question.
Just like the normal reason why things get smaller when you cool it?
No, it has to do with this. We've skipped the steps here, but basically free energy has an entropy and an enthalpy component, and you're changing that. As you go down lower, you're changing this. So I'm skipping some of the algebra here, but it's coming, basically your driving force for thermodynamics is getting stronger, but your surface area hasn't changed, right? So so again, if we go back here to our delta G expression, if this becomes even more negative, then this is going to happen at a smaller value. That's when it's going to have its maximum. So basically R star gets smaller. Okay? Thomas?
The temperature alpha beta is the temperature that's calculated from the phase diagram.
Yep,
T
exactly.
is and then T is the temperature that you're actually at.
Exactly. Yep. Bingo. So again, we call it a positive number because it's the amount of supercooling. So T alpha minus T, that's going to be a positive number. Say if that's 1200, but you're actually at 1100, then you have 100 degrees of supercooling. Yeah, Arthur?
At the end of the class, you said that water prefers to form the ice on the surface areas. Right?
Correct.
But then when you added that one term to the delta G, there's more surface area, but that still makes the delta G more smaller, more positive. So,
Okay, let's follow that logic for a minute. So we start out, let's say this first term is negative, meaning we're at a temperature below 0 degrees, so liquid water wants to turn into ice. We all agree on that. But then we say, in doing so, it's going to create surfaces, and that costs energy, so it doesn't want to do it. So there's this balance between these two things, right? So right now, because we've only considered homogeneous nucleation thus far, we said depending on what the shape of this thing is, we did it for a sphere so far, depending on the shape of this and how far below 0 we are, we can calculate just how big that critical nuclei needs to be, or in other words, just how much of an energy barrier there is. That's all we've done so far. Okay, other questions about this? Okay, let's do a calculation. Well, one more question, then a calculation.
Like the volume, the volume of atoms or
Good question. Let's clarify. So up here, this is the volume of a cluster of atoms, 4/3 pi r cubed. That's a bunch of atoms put together. And this delta GV, that's the molar volume, meaning in 1 mole of substance, how much volume does it take up? Okay? Okay, let's do a calculation on this. Let's do a sample one, right? So we'll do this for a clicker question, and it goes as follows. Let's say you have pure gold. Pure gold has a melting point of 1064 degrees Celsius, but in the laboratory, you find out, because you've got a little thermocouple sitting there in your molten gold, you find out that you can supercool it 230 degrees below its melting point. And this is possible. You can do this, like today, if we had a bunch of molten gold, we could do this, right? So then the question is, okay, given that you're 230 degrees below its its solidification temperature, melting point, right? Calculate R star for homogeneous nucleation, spherical particles, right? And the values you're going to need for this, you're going to need to know the latent heat of fusion and the surface free energy, which are given here, 1 in joules per meter cubed, 1 in joules per meter squared, and we want the answer, how big is your critical nuclei size in nanometers, so 1 times 10 to the negative 9 meters, with 1 decimal place. And let me show these formulas again. Okay, give that a shot. If you've got questions, we've got at least 1 or 2 TAs here today. Also, to get this to work out correctly, your temperature needs to be in Kelvin up here. This one's a difference in temperature, so it doesn't matter. Delta C, delta K is the same thing. But for absolute value, that needs to be in Kelvin. Yeah, another question? You're solving for R star. R star when your degree of supercooling is 230 degrees. That's delta H. Yeah, let me clarify. I've got the wrong one here. I forgot. I was going to have you calculate one or the other. Looks like the clicker question actually wants you to solve for delta G star, not R star. So same approach, just plug it into the second equation. I know. You got to do the maths again. Sorry about that. Yeah, Scar? T alpha beta, that's the transition temperature from thermodynamics where you expect the transition temperature. So for isomorphism, in this case, it tells you, it says the melting point tends to Turn that into Kelvin. And that's what you expect.
And then T would be our actual
T is the temperature where you're at. In this case, 230 degrees below you're at.
So the difference would be negative 1064.
It's a positive number 1064 minus something less. It's going to be a positive number. So if you left it in just as it was, it's going to come. Then there's electrons divided by the charge of the electron.
So it's 1.06.
1.608. Okay, we've just got a few minutes left, so why don't you get your answers in on this one? Because I asked you to do the wrong one, I'll make it correct, whatever you put in, but give this a shot, and then I want to save just a minute and work through it together. So get something entered. I'll make sure you get credit regardless, but enter something so I can end this. Okay, gonna wrap it up. Type something in. Okay, gonna wrap it up. Okay. Okay, so mostly some correct answer. Well, maybe a third of it correct. Let's go through it then. So again, I'll make this right regardless of what you put in, so you get your clicker points. How do we figure this out? So we'll work out the next one at the beginning of class next time where we solve for R star. The clicker question asks for delta G star, so let's do that. Delta G star is going to be 16 times pi times our surface energy, which is 0.132 joules per meter squared. And you'll want to keep your units. Again, leaving units off is by far the most common way I see people make mistakes, so leave your units in it. That is cubed. Then multiplied by the temperature where this is happening, squared. So what's 1064 in Kelvin? What is it? 1337? That is squared. This is now divided by 3 times negative 1.16 e to the 9th joules per meter cubed. That's squared. And then multiply this whole thing by 1 over 230 Kelvin squared. Okay? If you've done this right, you should end up with about 6 eV, but we'll go through the rest of the math at the beginning of class next time because we're out of time. Yeah, one last question? So one more question. I'll come answer. I can't quite hear you.